Hi students, welcome back to Excel Rapid Focus series. Today we are going to discuss haloalkanes and haloarenes, and this chapter has a weightage of 6 marks in the board exam. Here we're moving to first question. Here our first question is based on classification of halogen compounds. You know the first question, which of the following is an allylic halide? Tell me which is the answer. Very easy question. It's a normal question asked in last year board exam. See, very simple. Here, what's the condition for an allylic halide? For an allylic halide, halogen is connected to a single bonded carbon next to the double bond. This is an allylic halide. Here, halogen is connected to a single bonded carbon next to the double bond. This is also an allylic halide. Okay, this is also an allylic halide. A reason, halogen is connected to a single bonded carbon next to the double bond. So that condition is satisfying in the first option. You can say this is coming under allylic halide. Here you can see halogen is connected to a single bonded carbon next to the double bond. Then what about this option B? Yes, option B is coming under vinylic halide because halogen is directly connected to the double bond. If halogen is directly connected to the double bond, it's called vinylic halide. What about option C? Option C, we can say halogen is connected to a single bonded carbon next to the benzene ring, right? Halogen is connected to a single bonded carbon next to the benzene ring. So if this condition is satisfied, it is coming under benzylic halide. We learned already. Okay, this is coming under benzylic halide. Here halogen is connected to sp3 hybridized carbon atom, no double bond next to it. It is coming under normal alkyl halide. This is about the classification. The first question is, answer is allylic halide is option A. Then what about the second one? Which of the following belongs to the class of vinylic halide? Direct question. What is the condition for vinylic halide? Yes, condition for vinylic halide is halogen must be directly connected to the double bond. If halogen is directly connected to the double bond, it's called vinylic halide. Tell me which is the answer? Yes, halogen directly connected to the double bond is option C. So option C is coming under vinylic halide. This is alkyl halide. This is equal to allylic halide. You can say this is coming under vinylic halide. Okay, so option C is the answer. Now, IUPAC names of the following compound. You know what's the rule for IUPAC naming? Among halogen compounds, what's the rule for IUPAC name? You already studied. So the priority order you must know. According to the priority wise, carbon-carbon double bond is coming most. Then carbon-carbon triple bond is coming. Then alkyl group as well as halogen as well as alkoxy group as well as NO2 group. These all are having equal priority. These all are having equal priority, right? So whenever double bond and halogen is present, double bond has more priority, so we should give priority to double bond. Means we have to start number from the side nearest to the double bond. So here in this particular compound, you have halogen and double bond. Halogen is here, double bond is here. So we have to give priority to double bond, students. So double bond should be getting the less number, or you have to give less number to the double bond. So this is equal to number 1, this is number 2, number 3. Tell me the name now. Yes, we have to follow alphabetical order. According to the alphabetical order, bromine is coming first. That is 3 bromo, 1 chloro, then cyclohexene. That's the answer. Okay, so 3 bromo, 1 chloro, cyclohexene. Or you can say 3 bromo, 1 chloro, cyclohex, 1 ene. That's about the IUPAC name, right? Okay. So the next question we are talking now. The correct IUPAC name of CH3, CH3 twice, CHBr, CH3 is. So we have to expand the condensed formula. This is given in the condensed formula. You have to expand and try to do. How to expand? This is a compound CH3, C, CH3, again CH3, CHBr, CH3. So how to do the IUPAC name of this compound? See, we told you already, when halogen atoms are there, alkyl groups are there, we have to keep priority rule. We have to obey the priority rule. We know that this alkyl group, halogen, NO2, alkoxy group, they all are having equal priority, right? They all are having equal priority. When they have equal priority, what we will do? See, so here we have to start numbering from the side nearest to the branch. We have to start numbering from the side nearest to the branch. Here you can see, here bromine as well as methyl group all are having equal priority. So that time we have to consider we have to start number from the side nearest to more number of branches. So here you can see left side contain more number of branches. So we have to start numbering from here. This is 1, this is 2, this is 3, this is 4. Then we have to say the name according to the alphabetical order. So what will be the name? Can you tell me now? The name will be like this. What is the answer here? Yes, the name of the compound will be, you can say 3-bromo, 2,2-dimethyl butane. So option B is your answer, right? Option B is your answer. It should be 3-bromo, 2,2-dimethyl butane, right? That's it. I hope all of you got this, right? Okay. Then decreasing order of, next question, this is based on physical properties of halogen compounds. We are discussing that. Okay, decreasing order of boiling points of alkyl halide. You know, we studied already boiling point of alkyl halide. How boiling point is related, students? Tell me. Yes, the boiling point of alkyl halide, we know that this is the order of boiling point of alkyl halide. We know, we studied already, alkyl fluoride has less boiling point, then alkyl chloride, then alkyl bromide, then alkyl iodide. This is the order of boiling point we studied. Boiling point increases with the increase in molar mass. This is a method. Okay, boiling point increases with the increase in molar mass. So when molar mass increases, the van der Waals force of attraction between the molecule increases, which in turn increases the boiling point. So this is a direct question. The decreasing order of boiling point is alkyl fluoride, then alkyl chloride, then alkyl bromide, then alkyl iodide. Your answer is option A. I think all of you got it. This is a direct question. This was the board exam question. Okay, so we'll move to the next question. So, which of the following has higher melting point? This is a maximum time repeated question from this topic. You are all familiar with this particular question. So the answer is so easy. There are so many isomers of dichlorobenzene. Out of that, which one has high melting point, which one has high boiling point, that you have to remember. See, this is equal to 1,4-dichlorobenzene. This is 1,4-dichlorobenzene. That has high melting point. We'll discuss. Then this is equal to 1,2-dichlorobenzene. 1,2-dichlorobenzene. This is equal to 1,3-dichlorobenzene. This is equal to 1,3-dichlorobenzene. This is the order of melting point, students. We studied already. What is the order of melting point of isomers of dichlorobenzene? 1,4-dichlorobenzene has highest melting point. Then 1,2-dichlorobenzene. Then 1,3-dichlorobenzene. This is the order of melting point. Tell me why 1,4-dichlorobenzene has high melting point? Because 1,4-dichlorobenzene has a symmetry. Because of the symmetry, the molecule can be arranged closely in the crystal structure. When molecules are arranged closely in the crystal structure, we can see the attractive force between the molecule will increase. Automatically, the melting point will increase. See, students, melting point is a property of solid. In solid structure, melting point depends upon how closely molecules are arranged. Here, 1,4-dichlorobenzene can be arranged closely in the crystal structure. Because of the geometry is like that, we can arrange them so closely. Like this, we can arrange them so closely. This is equal to 1,4-dichlorobenzene. We can arrange them so closely. So the molecules attractive force will be more. automatically melting point will be more, right? Now, shall I ask one question? So the answer will be here, para-dichlorobenzene is the answer here. Para-dichlorobenzene is the answer. That is also called 1,4-dichlorobenzene. Tell me, which out of this will have high boiling point? Yes, that also you have to remember. Sometimes you may expect melting point. In board they may ask boiling points. Out of this, which isomer has high boiling point? Yes, students, high boiling point is here 1,2-dichlorobenzene. 1,2-dichlorobenzene overtakes 1,4-dichlorobenzene in terms of boiling point. So boiling point is a property of liquids. So in liquids, molecules are already a little bit far apart. So boiling point depends upon attractive force between the molecules in liquid form. That mainly depends upon polarity, students, polarity or dipole moment. So this molecule has more polarity as well as more dipole moment. So in liquid form, the attractive force between the molecule of 1,2-dichlorobenzene is greater than that of all other isomers. So boiling point, if we're talking about boiling point, 1,2-dichlorobenzene has slightly higher boiling point than all of them. Okay, that's it. I hope all of you got it, right? So we'll move to the next question. So assertion reason question we are talking, this is somewhat related to the dipole moment we will discuss. Okay, so assertion, CH3Cl has higher dipole moment than CH3F. A reason, CCl bond is longer than CF bond. Yes, we will discuss. Okay, yes. So we study dipole moment. What is dipole moment? Dipole moment is represented by the letter mu. Mu equal to Q into D. We know that. Charge into distance between charge. Okay, dipole moment of a particular covalent bond is equal to charge into distance between charge. Here, carbon fluorine bond is there. Carbon fluorine bond is there. In CH3F, you can see carbon fluorine bond. CH3Cl, you can see carbon chlorine bond, right? Yes, this is equal to, here the bond length of carbon chlorine bond is longer, students. Bond length is longer than CCl bond is longer than CF bond. So bond length more means the distance between two atoms. Bond length more means the distance will be more. Because of higher bond length, we can say the CH3Cl has higher dipole moment. Then you may ask one question, what about the charge? Yes, even though charge is slightly more in CF bond, the electronegativity difference between carbon and fluorine is more here. Carbon and fluorine is little more than that of carbon and chlorine. But no matter, the bond length is more. Because of the longer bond length, CH3Cl has higher dipole moment than CH3F. Remember that. Okay, here dipole moment of this molecule is found to be 1.86 dBi, and here it is equal to 1.84 dBi. So dipole moment of this particular molecule CH3Cl is little bigger because of more bond length. So this assertion is correct. No doubt, assertion is correct. What about reason? CCl bond is longer than CF bond. Yes, that's the reason why CH3Cl has high dipole moment. Reason is correct. So the option, assertion correct, reason correct. Option is coming as A. As per the Cbse, it will be option A, and that is correct. Explanation is there. Assertion correct, reason correct, correct explanation. So students, whenever you are discussing this question, you have to remember about order of dipole moment of this monohalogenated compound. That you have to learn. Sometimes they may ask. The order of dipole moment of these compounds are CH3I has least dipole moment. Then CH3Br is coming, CH3Br. Then CH3F is coming. Then CH3Cl is coming. You just go through this order. This is the order of dipole moment of monohalogenated product of methane. Okay, dipole moment, remember. So this is the answer for the particular question. I hope all of you got it. This is an important area. There is a chance, so go through it. Okay, so we are moving to the next question now. Yes. Consider the following a reaction. This is a compound. This is a last year board exam question. You have to identify the major product. See, what is this reaction? This is equal to free radical halogenation of alkane. We studied a reaction like that. This is equal to RH, alkane. We are treating it with chlorine or bromine. Chlorine or bromine in presence of UV light or sunlight. You will get a license to remove one of the hydrogen and bring chlorine or bromine there. So you will get a license to remove one hydrogen and keep bromine or chlorine over there. It can be chlorine or bromine over there. So this is called monohalogenated product. And this reaction is carried out according to the free radical mechanism, students. So the free radical mechanism is happening here. So you studied already this mechanism in 11th standard. According to the free radical mechanism, the major product obtained, you have to depends upon the stability of free radical. The stability of free radical you should know, then only you can apply which is the major product obtained, which is the minor product obtained. Accordingly you can discuss. Okay, so here we can say what is the order of major product obtained in free radical halogenation. Rough order I am giving so that you can apply. So the order of free radical halogenation is, you can say the order of free radical halogenation I am discussing here. Just wait. So the order will be benzylic halide. If there is a chance of forming benzylic halide, that will be the major product. Then allylic is coming, allylic, then allylic. Then tertiary is coming, then secondary, then primary, then vinylic, then aryl. This is the order of monohalogenated product obtained in free radical halogenation reaction. So how we are predicting this order? This order is obtained by checking the stability of free radical generated. Benzylic and allylic free radicals are stabilized by resonance. Okay, so benzylic halide will be the major product in free radical halogenation. So what is benzylic halide, students? Yes, the benzylic halide, I can say this is equal to benzylic halide. In benzylic halide, halogen is connected to a single bond carbon next to the benzene ring. In allylic halide, halogen is connected to a single bond carbon next to the double bond. In tertiary, other than halogen, there are 3 lines. It is connected to tertiary carbon atom. In secondary, halogen is connected to a carbon which is connected to 2 other carbon atoms. In primary, halogen is connected to a single bonded carbon and that carbon is connected to 1 other carbon. In vinylic, halogen is connected to a double bonded carbon directly. In aryl, halogen is connected to the benzene ring directly. This is the order of free radical halogenation of alkanes. Okay, so now considering this order, what will be the answer? Anybody can tell me? Yeah, this is so easy now. Now you can do now. Here there is hydrogen CH3. So whenever here we are, suppose we will discuss each and every answer. This answer A. Answer A is coming under secondary. Answer A is coming under secondary. So answer B is coming under tertiary because here halogen is connected to a single bond carbon. There it is connected to 3 other carbon atoms. Here this is primary because CH2X halogen is connected to a carbon which is connected to 1 other carbon. And here it is again secondary. So as per the rule, which is a major product, so easy now. The major product will be the tertiary one. So option B is the answer. Okay. This is the last year board exam question. Go through it. So just study this area. They are asking every time in board exam, they are asking the questions from this particular area. Okay. So one more question we will discuss from here. What is this? Which of the following will give single monochlorinated product upon treating with the chlorine in presence of UV? So what is the answer for this? See students, here also this question is also coming from free radical halogenation of alkane. So we can discuss the structure and we will decide. Okay. See now, what is cyclopentane? Cyclopentane is coming this way. This is equal to cyclopentane. What is 2,2-dimethyl propane? Yes, 2,2-dimethyl propane is like that. This is 2,2-dimethyl propane. 2,2-dimethyl propane. Okay. What is 2-methyl propane? 2-methyl propane. This is cyclopentane. This is 2,2-dimethyl propane. What is 2-methyl propane? Yes, 2-methyl propane is CH3, CH, CH3, CH3. This is equal to 2-methyl propane. Now, which will give single monochloro product upon chlorination? How to identify who will give single monochloro product? One small hint, students. Those compound which is giving single monochloro product will contain similar type of hydrogen atoms. Repeating, the compound which will give single monochloro product will contain similar type of hydrogen atoms. Yes. Here if I am talking about cyclohexapentane, this is CH2, CH2, this is CH2, this is CH2, this is CH2. Each and every carbon atom has similar type of hydrogen here. If chlorine is coming here, it is called 1-chlorocyclopentane. If chlorine is coming here, again it is called 1-chlorocyclopentane. If this hydrogen is replaced by chlorine, again it is called 1-chlorocyclopentane. So definitely cyclopentane will give single monochloro product. No doubt cyclopentane will give single monochloro product upon chlorination. Okay, upon chlorination we will get single monochloro product here. Here upon chlorination you will get a product this way. Yes, you will get a single monochloro product. A chlorine can come here, chlorine can come here, or chlorine can come here. Chlorine can replace any hydrogen. So you will get same answer only. That is called 1-chlorocyclopentane. And here this compound also we can check now. This compound, yes, we can check this compound. This compound also contain similar type of hydrogen atoms. Yes, 2,2-dimethyl propane contains similar type of hydrogen atom. So this also will give, single monochloro product. This also will give single monochloro product. No doubt about it. And what about this? This compound has different types of hydrogen atom. Different types of hydrogen atom. So this compound will give more than one type of monochloro product upon chlorination with the UV light. So the answer will be cyclopentane will give single monochloro product. 2,2-dimethyl propane will give single monochloro product. So we can say the answer is both A and B, right? The answer will be both A and B. This is your answer. Okay. So this is about the chlorination. So free radical halogenation of alkane is an important area. They're going to ask this. Okay. So we are moving to the next question. I hope all of you got it, right? Yes. Okay. So in alcohol, the next one we are talking about, the preparation part. In alcohol, the OH group can be replaced by Cl using SOCl2. The same reaction is not possible for phenol because, see what's the difference between alcohol and phenol? This is an alcohol, okay? CH3OH is an alcohol. This is an alcohol, right? Okay. This is a phenol. Phenol, condition of phenol is that OH group must be directly connected to the benzene ring. OH group must be directly connected to the carbon atom of the benzene ring, right? That's the thing. Now, see now, in phenol, we already studied before, phenol cannot do substitution like alcohols. We already did the reason also. The phenol is showing a particular property, students. The phenol structure, if I am talking about phenol structure, this is the structure of phenol, right? OH group, OH group. Now here, oxygen has 2 lone pair electron. We studied already, oxygen has 2 lone pair electron on phenol, and here you can say there is 2 lone pair electron over there. This lone pair electron is in conjugation with a double bond. It will show a resonance. So lone pair electron is in conjugation with a double bond. So phenol is showing a special resonance called plus R effect. We know that. Due to plus R effect, the outcome of resonance hybrid I am drawing, due to the resonance hybrid here, the resonance hybrid of phenol we already learned, this carbon oxygen bond in phenol has partial double bond in nature. Carbon oxygen bond in phenol has partial double bond in nature. Due to resonance, this bond become double bond. Because of that resonance, that carbon oxygen bond in phenol become shorter and stronger. Shorter and stronger. Because of that, phenol cannot do substitution. Phenol cannot do substitution. For example, if I am treating this one with SOCl2, you will get corresponding compound will be CH3Cl easily. But if I'm reacting this one with SOCl2, there will be no reaction. Reason is no reaction under normal condition. The reason is that the OH group cannot undergo substitution. The bond is so stronger and shorter because of what? Partial double bond arising due to resonance. So this is one of the important area. So the answer for this particular question is CO bond in phenol has partial double bond nature due to resonance. So this is your answer. Just go through it. Okay. So this is an important area. Just remember, this area is really important for the exam. Okay. So we are moving to the next question. I hope you got it right. So just go through it. Next one we are talking. The synthesis of alkyl fluoride is best obtained from. We know we studied so many methods. We can prepare aryl fluoride using diazonium salt. We can prepare alkyl fluoride using a particular reaction. Can you name the reaction? What's that name reaction? That is equal to, we can say, Schwarz reaction. What is Schwarz reaction? Yes, you have an alkyl halide here. Alkyl halide. That halogen can be chlorine or bromine. If you are treating it with any fluorinating agent like AgF, you can replace halogen by chlorine or bromine by fluorine. Chlorine or bromine by fluorine, right? That is equal to, we can say, Schwarz reaction. Instead of AgF, you can use some other fluorinating agent like COF2. We can use Hg2F2, etc. SbF3, etc. Remember. So this fluorinating agent can replace halogen, chlorine or bromine by fluorine. This is an example of nucleophilic substitution reaction. So this cannot be used for preparation of aryl halide. This is used for preparation of alkyl fluoride. So alkyl fluorides can be prepared by using Schwarz reaction. This reaction is equal to Schwarz reaction. Here byproduct will be AgX. Go through it. Okay, so Schwarz reaction is the answer for it. So preparation of alkyl fluoride is done by Schwarz reaction. If you want to prepare fluorobenzene, you can't use this reaction because this is an example of nucleophilic substitution reaction. Aryl halides cannot undergo nucleophilic substitution reaction. We already studied before, right? So we are moving to the next question. I think this is easy question. We are moving to it. The next one we are talking. Iodination of benzene or toluene is done in presence of HNO3 or HiO4 because this is a reader question. This is a reader very important topic. So they are asking this. So now what is the answer for this? What is iodination? Iodination, we studied already preparation of aryl halides. We can prepare aryl halide by direct halogenation of benzene or toluene or any other aromatic hydrocarbon possible. So for example, if you have benzene, we are treating it with the chlorine in presence of FeCl3 or even FeCl3 in dark condition. What is an answer? Yes, you will get an answer. You will get chlorobenzene, right? You will get chlorobenzene here. Here this type of reaction is equal to electrophilic substitution reaction or ring substitution reaction. Here Cl plus will generate, Cl plus will attack here, H plus is going out, H plus will combine with the other Cl minus to get Cl plus and Cl minus will generate, H plus will combine with the Cl minus to get HCl. Now what is iodination? Yes, we can do iodination similar method. Yes. So, but iodination, what's the problem with iodination we are discussing? You can do iodination of toluene, you can do iodination of benzene. Suppose I am doing iodination of benzene, this is equal to benzene. We will treat with iodine in presence of Fe and Fe in presence of Fe. We can treat iodination in presence of Fe or Fe. I3, no issue. So you will get in presence of Fe. You will get iodobenzene. You will get iodobenzene, right? Iodobenzene. No doubt, you will get iodobenzene. And byproduct will be Hi. Like that here, Cl plus and Cl minus will generate. Cl plus will attack here. Cl plus will attack here. H plus is going out. H plus will combine with the Cl minus to get HCl. Same way, here H plus will combine with I minus to get Hi. Here I plus and I minus will generate. See, I plus will come here. H plus will combine with I minus to get Hi. See students, this reaction, one property of this reaction is that this reaction is reversible. When this reaction is reversible, what happened? You know, you heard about reversible reaction. What happened to if the reaction is reversible? Yes, if the reaction is reversible, they can revert it back. So you may not get iodobenzene easily because the reaction is reversible. If the reaction is reversible, the mixture may contain benzene and iodobenzene. The reaction may not be completed. Okay, so we have a one method now. What we are removing this HI. We are removing this HI by using an oxidizing agent. So the oxidizing agent used for this purpose is HNO3 as well as HiO4. Okay, you can say HiO4. Remember. So oxidizing agent used for this particular thing is nitric acid as well as HiO4. Meta-periodic acid. HiO4 is called meta-periodic acid. So you can use this oxidizing agent to convert Hi to I2. Hi get oxidized to I2 here. When Hi is converted into I2, students, what will happen here? See, Hi is converted into I2. When Hi is converted into I2, so the backward reaction is not possible. According to the Le Chatelier principle, if you are removing one of the product, you can see that the reaction cannot be reverted. The forward reaction rate will increase. So if I am removing one of the product, here Hi is converted into I2. So it cannot go for backward reaction. So we can increase the yield of iodobenzene by using HNO3 and HiO4, because HNO3 and HiO4 oxidizes Hi generated to I2. Hi generated to I2. So we can say the answer is to prevent the backward reaction by oxidation oxidizing Hi to I2. So this is the answer. Okay. So option C is the answer. I hope all of you got it, right? So just go through this portion, right? Okay. Next question we are moving. Now we are talking about something about optical activity, optical isomerism and everything. We study like that. What is the condition for optical activity, optical isomerism and everything? See, wait, just we'll discuss this question. In which of the following molecule carbon atom marked is chiral? This is a last year board exam question. So easy question. This is the simplest question. We know already. You already studied this topic, right? So what is a chiral carbon atom? See, students, the chiral carbon atom is the carbon atom where 4 different groups are connected to it. If a carbon atom has 4 different groups, it is called chiral carbon atom. See, this particular carbon, the first carbon, you check this carbon. This has 4 different groups. 1, 2, 3, 4. All groups are 4 different groups. This particular carbon, iodine, chlorine, bromine, D. What is this D? D is nothing but deuterium. You studied isotope of hydrogen. Hydrogen is mentioned as H. Deuterium, heavier isotope of hydrogen, is called deuterium. That is called D. D is nothing but deuterium, students. Don't worry about it. So these all groups are different. Deuterium, iodine, chlorine, bromine. All 4 groups are different. So we can consider this as a chiral carbon. This also chiral carbon. And what about this? Here you have OH. Here you have CH3. Here you have CH2, CH3. Here you have D. This also chiral carbon. What about this? Yes, in this particular compound you can see these 2 groups are same. These 2 groups are same. So this cannot be chiral. So the answer will be first one, second one and third one. So the answer is number 1, 2 and 3rd. Which of the following marked is chiral? The answer is 1, 2 and 3rd. Option A. This is the simplest question. Go through it. Chiral carbon atom is really important. So we are moving to the next question. Okay. See, an organic molecule necessarily shows optical activity if it is. See, what is the condition for optical activity? We learned that. There are 2 conditions for optical activity. Anyone you have to follow, right? Number 1 is that the compound must contain chiral carbon atom. Okay, the compound must contain chiral carbon atom. Compound must contain chiral carbon atom. Contain chiral carbon atom. We studied already what is chiral carbon atom. So compound must contain chiral carbon atom. Second condition or other condition we can say, the compound must have absence of symmetry. Compound must be asymmetry or absence of symmetry. Absence of symmetry. Okay. if a compound has absence of symmetry, the compound will show optical activity. So the condition for showing optical activity is that number one, you can say must contain chiral carbon atom, or the compound must have absence of symmetry. These are the two conditions. Okay, if a compound has chiral carbon atom, the compound will have no symmetry. So the absence of symmetry is nothing but presence of chiral carbon atom. Some compounds are there, they have no chiral carbon atom, still they are optically active because they have absence of symmetry. See, if I am talking about our palm, this palm, you can see there is no symmetry here. You can't divide this palm into two equal half. No. Here if I am dividing this way, you will not get two equal half. Never. If I am dividing this way, you will not get two equal half. If I am dividing this way, okay, suppose you are cutting from here, you are cutting from here, you may not get equal half. So the palm you can see is an object with the absence of symmetry. So if a molecule has similar type structure, this will show optical activity, right? Now one more thing. Those who have absence of symmetry, students, they will form non-superimposable mirror images. They will form non-superimposable mirror images. So if a molecule has chiral carbon atom, or if a molecule has absence of symmetry, the molecule will show, we can say, yes, it will form non-superimposable mirror images. So all optically active compounds form non-superimposable mirror images. What do you mean by non-superimposable mirror images? See, I will give you one example. Okay, yes, I have a compound with the carbon here. This is equal to CH2CH3. This is equal to CH3. This is equal to, we can say, H. This is equal to Br. This is a chiral carbon atom. If I am talking about the mirror image of this particular compound, the mirror image, if I am talking about the mirror image you will get, this is a mirror image I am drawing here. This is equal to CH2CH3. This is equal to H over here. This will be H over here. This is H. This is equal to Br over here. Br. This is equal to CH3 over here. This is a object. This is a mirror image. If I am taking the mirror image and placing over the object, it will not coincide. Such mirror images are called what? Non-superimposable mirror images. See, our left palm and right palm, they are mirror images to each other. Suppose you lost your left palm with an accident. If you want to see a left palm, just stand in front of mirror, show the right palm, the mirror image will be left palm. So remember that. So left palm and right palm, they are mirror images to each other. This is the object thing like that. This is a mirror image. If I am placing the mirror image over the object, it will not coincide. So these two are called, this type of mirror images and object are called, they will form non-superimposable mirror images. So any compound who is optically active will contain either chiral carbon atom or absence of symmetry. They will form non-superimposable mirror images, right? So we can say an organic molecule necessarily show optical activity if it contain asymmetric carbon and B, a non-superimposable on its mirror image. So we can go for this. Okay, we can go for this. The best option here, it is equal to either A or B. Either A or B. So if a compound has chiral carbon, the compound will be optically active. If a compound can form non-superimposable mirror images, meaning the compound is asymmetric, compound has no symmetry, so compound will show optical activity. So remember that. Okay, so we are moving to the next question now. See, the following reaction, in the following reaction, name the process if only B is the product obtained. This is a reader solved topic inside the reader. They can ask question from that. Remember, just go through it. I'll tell you what is this. Okay, what is inversion of configuration? What is a retention of configuration? What is racemization? Most of the students have a lot of confusion regarding this particular topic. See, what is configuration? arrangement of atoms around chiral carbon atom in space is called configuration. Repeating, arrangement of atoms around chiral carbon atom in space we call it as configuration. Or arrangement of species around a center in space is called what? Tell me. Configuration. See, the left palm has a particular configuration. The arrangement of fingers in space is equal to configuration. Right palm, yes, you have different configuration here because the arrangement of fingers in space of left palm and right palm, they are different. They have different configuration, right? So they have different configuration. How to decide which configuration is R, which configuration is S, that is beyond your level. It is not in Cbse. I am not discussing that. See now here how to decide whether whether configuration change is happening, inversion is happening, or retention is happening. What is this process? Very simple logic. Think like that. You have a compound with the chiral carbon atom undergoing substitution reaction, undergoing nucleophilic substitution reaction. If a compound with the chiral carbon atom undergoing nucleophilic substitution reaction, it may include inversion of configuration, it may include retention, it may include both, everything. So we will discuss what is inversion, what is retention. Wait, here you can see in this particular compound the X is replaced by Y. This is a nucleophile, the Y is replacing X. Here also X is replaced by Y. Remember now, we will compare both. Here the product, this is the product, this is the reactant, this is the reactant, this is the product. So in this reactant and product, the arrangement of groups surrounding this chiral carbon, this is the chiral carbon, arrangement of groups surrounding this chiral carbon. Students, see that chiral carbon. Arrangement of groups surrounding the chiral carbon atom is same only. Here X is just replaced by Y. This is called, if this is the product, we can call it as there is no change in configuration, no change in the arrangement of atoms in space. Here X is replaced by Y. All other groups are arranged similar way in space as a reactant. So there is no change in the arrangement of species in space. So if product A is there, it is called retention of configuration. Now see, this is a reactant, this is a product. Here you are getting a product which is similar, almost similar to the mirror image. Here the product obtained is almost similar to the mirror image, students. So when product obtained is almost similar to the mirror image, we call it as it involves inversion of configuration. Okay, so when product obtained is almost similar to the mirror image, we call it as inversion of configuration. So if product B is generated, we call it as it involves inversion of configuration. You can see here X, and here if I am keeping this Y as X over here, it will be just like a mirror image. So this product is almost like a mirror image. So this one involves inversion of configuration. Now if you have both together, inversion and retention together, that is called racemization. So three things you have to remember here. This is an important area. If product A is the answer, that involves a retention of configuration. If product B is the answer, that involves inversion of configuration. Inversion and retention together, we call it as a racemization, right? So in this particular question, name the product B. B means it is inversion of configuration. If product B is there, it involves inversion of configuration. So the answer is B. Any question can come. Go through the concept, understand the concept well. If your concept is clear, you can do any question. Just study this. Okay, this is an important area. Go through it. So we are moving to the next question. Assertion. Allyl chloride is more reactive than normal propyl chloride towards hydrolysis with aqueous NaOH. Reason. Allyl chloride halogen is connected to sp3 hybridized carbon atom. See, we studied already there are two types of nucleophilic substitution reaction. One is called SN1 reaction, other one is equal to SN2 reaction, right? We studied already. So in SN1 reaction, what is happening? We already discussed, I am not talking about much. Just I am discussing the questions only. Here, allyl chloride is more reactive than normal propyl chloride towards hydrolysis with aqueous NaOH. Okay, remember. Something I will tell you about SN1. Okay. See, normally in SN1 reaction, you have to remember very important area. The hydrolysis is called polar. Hydrolysis means the solvent is water. Aqueous NaOH. Solvent is water. When solvent is water, students, it is called polar protic solvent. Polar protic solvent favor SN1 reaction. Repeating, hydrolysis indicates hydrolysis is an example of polar protic solvent. Polar protic solvent, right? Polar protic solvent. So polar protic solvent favor SN1. Favor SN1, right? Favor SN1. See, why polar protic solvent favor SN1? Simple. So polar protic solvent stabilizes the nucleophile leaving group, stabilizes the nucleophile which is leaving group. See, for example, we can say this is the reaction happening. This is equal to RCl or RX, I can say RX. On treating it with the OH minus, you will get ROH plus X minus. This is equal to leaving group. Okay. So if you have a polar protic solvent like water, alcohol, etc. Water is an example of polar protic solvent. Alcohol is another example of polar protic solvent. Protic solvent means which contain hydrogen, okay, which contain hydrogen, H plus, which can generate H plus. The solvent which can generate H plus are coming under protic solvent. So polar protic solvent indicates the solvent which can generate H plus. Okay. So water is a polar protic solvent. Alcohol is also coming under polar protic solvent. So these all solvent interact with the leaving group. They stabilizes the leaving group. Suppose this is X minus is interacting with the water. It stabilizes the X minus. Interaction with the water, it stabilizes the X minus. So the interaction may be dipole attraction, or interaction may be hydrogen bond, etc. So the leaving group is stabilized by the interaction. So carbocation formation become little more easy. That's the slowest step in SN1 reaction. So we studied already SN1 reaction. You know, the formation of carbocation is the slowest step in SN1 reaction. That become little faster in presence of polar protic solvent, because polar protic solvent stabilizes the leaving nucleophile by interacting with the leaving group here. This is a solvent. The solvent will interact with the leaving group and stabilize it. So the first step become little faster. So the reaction become SN1. So repeating again, very simple logic. If you're finding hard, just remember this: hydrolysis favor SN1. That's it. Hydrolysis favor SN1. So allyl chloride is more reactive than normal propyl chloride towards hydrolysis with aqueous NaOH. Is correct, because in SN1 reaction we studied already. This is the information you have to remember. In SN1 reaction, repeating before going to the next topic, just repeating, polar protic solvent favor SN1. That you have to remember, right? Now what is SN1? Which is more reactive towards SN1? Order of reactivity I am talking. Okay. Yes. Order of reactivity we are talking. What is the order of reactivity of SN1 reaction? See, students. Order of reactivity is reactivity of SN1. Remember, reactivity of SN1 is directly proportional to stability of carbocation. Stability of carbocation. Right? That's very, very important. Stability of carbocation. Got it? So stability of carbocation, maximum stable carbocation is benzylic. Benzylic halides are more reactive. Benzylic carbocation is more stable. Then allylic. Okay. then tertiary, then secondary, then primary, then vinylic, then aryl. This is the same order as free radical halogenation. This is the same stability as free radical, in halogenation of alkane. We are getting a monohalogenated product. There we studied one order. This order and that order is same only. There we are talking about stability of free radical. Here we are talking about stability of carbocation. So benzylic carbocation is more stable than allylic. Allylic is more stable than tertiary, secondary, primary, vinylic, aryl. This is the order of stability of carbocation, right? This is the order of stability of carbocation, or this is the order of stability of carbocation, or this is the order of reactivity of halogen compounds towards SN1. If I'm talking about halogen compound, it will be allylic halide will come, tertiary halide will come, secondary halide will come, primary halide will come, vinylic will come, then aryl will come. See now. So these two are stabilized by resonance. Allylic and benzylic halides are stabilized by resonance. See now, wait. We can say now the question. Now we are talking about the question now. See, assertion. Allyl chloride. What is allyl chloride? Allyl chloride is equal to CH2 double bond CH single bond CH2Cl. This is called allyl chloride. Okay. What is normal propyl chloride? Yes, normal propyl chloride I am talking. What is normal propyl chloride? CH3, CH2, CH2Cl. This is called a normal propyl chloride. Now see, this normal propyl chloride is a primary halide. It's a primary halide. Okay. This is primary allylic. This is allylic as well as primary allylic. This is allylic. Condition for allylic halide we already studied. Halogen is connected to a single bond carbon next to the double bond. So this is equal to allylic halide. So as per the rule, allyl chloride is more reactive than normal propyl chloride towards hydrolysis, means towards SN1. So this is correct. Assertion is correct. Allyl chloride is more reactive than normal propyl chloride towards hydrolysis with aqueous NaOH. Assertion is correct. No doubt. Assertion is correct. The reason for that particular assertion is that because allylic carbocation is more stable than primary carbocation, right? Allylic carbocation is more stable than primary carbocation. That's the reason for that particular question, right? But here reason given it is different. Allyl chloride halogen atom is connected to sp3 hybridized carbon. Yes, this is called sp3 hybridized carbon. This is called sp3 hybridized carbon, students. This carbon atom over here is equal to sp3 hybridized. This is sp3 hybridized carbon. So in allyl chloride, halogen is connected to sp3 hybridized carbon. Yes, correct, no doubt. So allyl chloride, halogen is connected to sp3 hybridized carbon. So the reason is correct. Reason is correct, right? Reason is correct. Assertion is correct. Reason is correct. Assertion correct. Reason correct. But not the correct explanation. Okay, not the correct explanation. So the option will be B. The answer for this one, option will be B. Assertion correct. Reason correct. Not the correct explanation. The reason why allyl chloride is more reactive towards hydrolysis. Reason in shorter way, hydrolysis favor SN1. In SN1, reactivity is directly proportional to stability of carbocation. Allylic carbocation is more stable than normal propyl carbocation. This is the reason. Just go through it. This topic is coming in the exam. This is a board exam question which came before. So remember, this area is really important. Now we are moving to the next question. Okay. Hope all of you got it. This order of reactivity of halogen compounds towards SN1, you have to remember. Okay. Now, this is another question. Consider the following bromide. The correct order of reactivity of SN1 is dash. See this question, we will classify them into different category now. See now, this is equal to, we are classifying, we just studied this concept already. This is equal to primary halide. This is primary halide. This is allylic. This is allylic because halogen is connected to a single bond carbon next to the double bond. This is allylic. This is allylic, but it is secondary allylic. It's allylic also, secondary also. This is equal to secondary halide. This is equal to secondary halide. We know the order of reactivity. Just now we discussed allylic is more reactive towards SN1, then secondary, then primary. So the answer will be B will be more reactive, okay, then C, then A. B will be more reactive, then C, then A. This is your answer. I hope you got it. Just now we discussed in SN1 reactivity order is that allylic is more reactive than secondary, and the secondary is more reactive than primary towards SN1 reaction. Okay, just study that order and do it. This is answer is B, then C, then A. Okay, hope you got it right. Okay, next one we are talking which one of the following compounds is more reactive towards SN1 reaction. This is also one of the board question. Most of the students are struggling here, so we will see now we will write everything and we will discuss the answer here. SN1 order of reactivity we already studied, right? SN1 order of reactivity we already studied. This is coming under allylic. Option A, we will see option A, CH2 double bond CH, CH2Br. This is allylic, no doubt. This is allylic, no doubt. What about option B? Option B is benzylic. Option B, C6H5 CH2Br. This is nothing but benzene ring with the CH2Br. This is benzylic. This is benzylic primary. Benzylic primary. We know that this is primary halide. Then what about C? Option C we are talking. What is C? Option C. Option C I am writing here. This is C6H5 CH C6H5Br. C6H5Br. What is the meaning of that? Yes, you have a benzene ring with the CH, Br here with another benzene ring. This is the expansion of C. See, whenever we are expanding, you will get this. Okay. What is the option D? Option D I am writing here. Option D is like that. C6H5 CH CH3Br. CH3Br, right? So the answer will be benzene ring with the CH CH3Br. So this is the different options. Now confusion is that, sir, we studied benzylic is more reactive than allylic. So this will be more reactive than this benzylic is more reactive than allylic, no doubt. This is also now which are all benzylic here, see students. This is called benzylic. This is called benzylic. Benzylic, right? This is benzylic. Remember, this is benzylic. This is also benzylic primary, right? We already learned. This is equal to benzylic secondary. This is benzylic tertiary. Sorry, benzylic secondary itself. Okay, this is benzylic secondary itself. This is benzylic secondary. So this is benzylic secondary. This is benzylic secondary. This is benzylic primary. No confusion. See, in SN1 reaction, benzylic halides are stabilized by resonance. No doubt, benzylic halides are stabilized by resonance. So, whenever more number benzene ring is present in benzylic halide, it is stabilized more. So, it is more resonance stabilized. Here, this guy is more resonance stabilized than this, and this is more stable than this. This carbocation will be more stable. Here, order of reactivity, if I am talking, A will be least reactive. Then who will come? After that, B will come, B will come. Then after that, D will come. After that, D will come. And the most reactive will be C. The reason is these two are benzylic secondary. These two are benzylic secondary. This is benzylic primary. This is allylic. Now you may be confused with the benzylic to secondary. See, very simple logic. Among different benzylic halide, if you have more number of benzene ring, like this, more number benzene ring, that particular halide will be more stabilized by resonance. That's very, very important. So this particular benzylic halide is more stabilized by resonance. So that particular carbocation formed by that halide will be stabilized by resonance. Okay, so carbocation formed by this secondary halide is more stabilized by resonance. So in benzyl halide, if you have more number benzene ring, that particular halide will be more reactive in SN1. Keep it in your mind, it is very, very important. So the answer will be, most of the reactive is this one. C is the answer. Okay, option C is your answer, students. Remember, option C is your answer. Go through it. This is a little difficult question. Just go through it. Okay, remember, this is very important. This one came in board exam before. Okay, yes, we are moving to the next question now. Now the next question is, which will undergo SN2 reaction fastest among the following compounds? See, that is very important topic. So which will undergo SN2 reaction faster? See, we know that SN2 reaction takes place in single step, proceeds to the formation of carbocation. So the reactivity of SN2 is inversely proportional to steric effect. We learned that. Reactivity of SN2, the reactivity of SN2 inversely proportional to what? Steric effect. Okay, reactivity of SN2 is inversely proportional to steric effect. This is very, very important thing you should remember. So the reactivity of SN2 is inversely proportional to steric effect. Steric effect we already learned. Nucleophile will attack the carbon atom from behind. The repulsion experienced during the attack is called steric effect. So order of reactivity we studied already. What is the order of reactivity of SN2? Primary, then secondary, then tertiary, like that. This is the order of reactivity of SN2. Primary, secondary, tertiary. Then aryl is coming. Aryl is least reactive. Vinyl and aryl. Aryl is least reactive among SN2, right? Aryl is least reactive in SN2. So remember, primary most reactive, secondary, tertiary, aryl. And here methyl will be the most reactive one because it has least steric effect. Among all halogen compounds, methyl halide has least steric effect. So this is the order of reactivity of SN2 we learned before. Now the question is not based on here. Here all are primary. Fluorine is there, bromine is there, halogen is there, iodine is there. When all are primary, so different halogen atoms are there. One more thing you have to remember, in all reactions, whether it is SN1 or SN2, the order of reactivity of halogen compounds in SN1 as well as SN2 or any other reaction. Okay, this is the order of reactivity. Alkyl bromide, alkyl iodide, alkyl bromide, alkyl chloride, alkyl fluoride. This is the order of reactivity of halogen compounds in every reaction. If this order is same for SN1, this order is same for SN2, this order is same for the reaction with the metals, this order is same for dehydrohalogenation. So whenever you have a halogen compound, students, remember this particular point. The order of reactivity of halogen compounds in any reaction, whether it is SN1, whether it is SN2, whether it is reaction with the metals, whether it is the dehydrohalogenation or beta elimination, the order of reactivity is like that. Alkyl iodide is more reactive than alkyl bromide, then alkyl chloride, then alkyl fluoride. Okay, so this is the order of reactivity. Tell me why alkyl iodide is more reactive. See students, this is carbon iodine bond is there. Carbon iodine bond. The carbon iodine bond is a weaker bond, because carbon and iodine, the size difference is so much. So here the carbon is a small guy, iodine is a gigantic guy. They are making a bond between each other. The bond formed will be, weaker bond due to the size difference over there, right? So this bond is weaker. So because of the weaker bond, you can see students, the weaker bond will make the I minus to leave easily. So I minus will be a better leaving group because of weaker bond over here. In other language, we can say carbon iodine bond has low bond dissociation enthalpy. Carbon iodine bond has low bond dissociation enthalpy. So students, remember, in every reaction, whether it is reaction with the metals or any other reaction, the reactivity is maximum for alkyl iodide. Reason, carbon iodine bond is weaker bond, I minus is a better leaving group, or carbon iodine bond has low bond dissociation enthalpy. Remember these all. Okay, so the answer will be very simple. Answer will be D. Okay, option is D, students. You can check the option will be what? D, right? The option is D. Go through it. This is an easy question. Just remember this all. SN2 order of reactivity you have to remember. Primary, methyl more, primary, secondary, tertiary, aryl. Okay, remember that. This is the order of reactivity of SN2. Okay, that's it. We are moving to the next question now. Consider the following reaction compounds. The correct order of reactivity of SN2 is dash. See, you have to identify whether it is primary, secondary, or tertiary, or aryl, like that. See now, very simple. This is equal to secondary halide. The reason, halogen is connected to a carbon which is connected to two other carbon. This is coming under secondary. We learned that. Halogen is connected to a carbon which is connected to two other carbon. So this is called the primary, because primary identity is CH2Cl. If CH2X is there, it's called the primary. So this particular compound is coming under primary because CH2X is here. This is called the primary, this is called secondary. And what about this? This is equal to, we can say, aryl. This is equal to aryl. Okay, aryl. So we can say this is equal to aryl. Yes. Now this is aryl halide. This is primary, this is secondary. Now you can get the answer. We already said it. The correct order of reactivity of these compounds towards SN2 is primary will be maximum, so second is maximum. Then secondary will come, that is first. Then aryl will come, that is third. So the answer is C. Okay, very easy question. Just go through this is a board exam question, remember. So just study it. Okay. So this is equal to order of reactivity, aryl, primary, secondary. The order of reactivity is like that. Okay, so this is about order of reactivity of SN2. So we are moving to the next question. Hope you got it, right? Yes. In a substitution reaction of the type RBr plus Cl minus giving DMF, you will get RCl plus Br minus. So this is a reaction. One nucleophile replaces the other nucleophile. Which is more reactive? So this question is a bit harder in Cbse. You have to remember one more point here. Here we have to check the solvent, right? Who is the solvent over here? Tell me. The solvent here, it is equal to DMF. What is DMF full form? DMF. DMF is equal to NN dimethyl formamide. The name of the compound DMF, dimethyl formamide. You can remember. This is H, C double bond O, N, CH3, CH3. This compound is equal to DMF. This is a polar aprotic solvent. Polar aprotic solvent. Polar aprotic solvent, right? So polar aprotic solvent. So DMF is equal to polar aprotic solvent. What do you mean by aprotic solvent? Aprotic solvent cannot generate H plus ion, right? So polar aprotic solvent cannot generate H plus ions. So polar aprotic solvent favor SN2. So by checking the solvent, you can see, students, by checking the solvent, here the solvent is DMF. When you have a DMF, say polar aprotic solvent, the mechanism will be SN2. So they are indirectly asking which of the following is more reactive towards SN2. That's a question. Okay. So which are all other polar aprotic solvent? Yes, you have to remember acetone is another polar aprotic solvent. Acetone. Another polar aprotic solvent is equal to DMSO, DMSO, dimethyl sulfoxide. Dimethyl sulfoxide, acetone is CH3, C double bond O, CH3. Dimethyl sulfoxide is like that, CH3, S double bond O, CH3, this is equal to dimethyl sulfoxide. These are all polar aprotic solvent, the solvent which cannot generate H+. So polar aprotic solvent favor SN2. Previously we studied polar protic solvent favor SN1. Here polar aprotic solvent favor SN2. How? See now. If you have aprotic solvent, it increases the nucleophilicity of attacking reagent. We have a nucleophile. In SN2 reaction, we studied already, nucleophile is coming and attacking from behind. Okay. So, if you have a polar aprotic solvent, the nucleophilicity will be increased. Suppose you have X minus here. X minus is attacking the carbon atom over here. This is the carbon atom you have. This is the carbon atom you have. This is the halogen compound you have. Yes, this is the halogen compound. This is a carbon atom. Now it is attacking here. Ability of attacking of X minus to carbon atom. Ability to attack this X minus to carbon atom. We call it as nucleophilicity. Very simple. The X minus is attacking the carbon. The ability of X minus to attack the carbon is called nucleophilicity. So that will be increased if you have polar aprotic solvent is here. Why? Simple. Here, if you are using polar protic solvent, the X minus will interact with the polar protic solvent so that it will not behave as better nucleophile. So there will be interaction of solvent with the X minus. Now here, if you are using polar aprotic solvent, interaction with the solvent will be less, so that X minus will behave as nucleophile. So it will increase the ability to attack X minus on carbon atom. In other way, it will increase the nucleophilicity, and which in turn increases the rate of SN2 reaction. So this is the answer. So polar aprotic solvent favor SN2. Remember that. So which are the polar aprotic solvent? But this is not given in the Cbse and may not come. Sometimes it can come. It depends. So this is the answer. So now tell me, which of the following is more reactive towards SN2? Tell me, which of the following is more reactive towards SN2? SN2 more reactive is primary. So this is primary. This is also primary with the branch. This is primary with less number carbon. If you have so many primary, which is the most reactive in SN2? So simple. Listen students, the most reactive is the primary with the less number of carbon. Less number of carbon, straight chain. Primary with less number carbon, straight chain will be the more reactive one. So this is the answer. It has less steric effect, right? So the option D will be the answer here. DMF, repeating again, DMF follow SN2. DMF is a polar aprotic solvent. Polar aprotic solvent favor SN2 mechanism. In SN2, the more reactive one is the primary with the less number carbon or straight carbon. Okay, primary with the straight chain with less number carbon. That will be the more reactive one. So the answer will be D. Okay, so we are moving to the next question now. See. The final product in the following reaction is, what is the final product in the following reaction? See, very simple. This reaction is so simple, we are discussing now. We already studied. So CH3OH, on treating it with PBr3, what is the answer? OH will be replaced by bromine. We studied this is the preparation of halogen compounds. We studied. So PCl3, PBr3, we can prepare halogen compounds. So the answer will be CH3Cl. Then CH3Cl on treating it with AgCN, the major product. We know that. We heard about ambident nucleophile and everything. Tell me which is a major product here. So easy. The major product will be corresponding isocyanate. The answer will be CH3NC. CH3NC. If you are using, you study like that, you have RX on treating it with KCN. KCN, the major product will be nitrile. Or NaCN, the major product will be nitrile. If you are using AgCN, remember students, the major product will become what? Isocyanate or carbylamine. Isocyanate or carbylamine. Here the answer will be CH3NC. The answer is A. Option A is your answer. Okay. Option A is your answer. Remember that. So in the here answer is isocyanate. It's an easy question, so go through it. Okay, so we study like that. With Rx on treating with the KCl or NaCl, you will get nitrile as major product, cyanide as major product. Same thing on treating with AgCl, you will get isocyanate as major product. Go through it. That's about 22nd question, right? Now the next question is that this one came in last year board exam question. This is a last year board exam question. This is one of the reaction with the metals. We study reaction with the metals, Grignard's reagent, formation of Grignard's reagent, Wood's reaction, Wood's-Wittig reaction. These all we studied. This is one of the question from Grignard's reagent. You have to remember a small topic here. This is equal to halogen compound, Rx. On treating it with Mg in dry ether, Mg in dry ether, students remember, Mg in dry ether, Mg will come in between R and X. If you have Rx, on treating it with Mg in dry ether, Mg will come in between R and X. You will get RMgX, RMgX, okay. Rx on treating it with Mg in dry ether, you will get RMgX, right? RMgX is the answer. See now, Rx on treated with Mg in dry ether, you will get RMgX. Then what is next? This RMgX on treating it with the H2O or any species which can generate H+, right? But you will get even alcohol, okay, in presence of alcohol also. So RMgX on treating it with water or in presence of H+, what will happen? See student, very simple, okay? The simple thing is that this RMgX, I can say here the MgX is replaced by, the MgX is replaced by H. MgX is replaced by H. MgX plus is replaced by H. So you will get RH. This is your answer, right? So this is the answer. So now coming back to this topic. So what's the answer here? Tell me. Yes, we have a compound now. This answer will be, first compound will be, this is equal to cyclobutane with bromine, bromocyclobutane. We are treating it with Mg in dry ether, Mg in dry ether, Mg in dry ether. You will get cyclobutane with the MgBr, cyclobutyl magnesium bromide. On treating it with water, just remember very simple logic, replace MgX by H. So you will get cyclobutane. You will get cyclobutane. Here whenever we are writing MgBr is replaced by H, we won't write H in bond line notation. So the answer will be cyclobutane. So the answer option is simple. The option is cyclobutane, right? That's about this question. I think all of you got it. This is an important question. Remember, this is last year board exam question. Okay. Next one. The reaction given before. This is the reaction given below. Chlorobenzene plus 2Na plus CH3Cl will get toluene. What is the name of this reaction? This is also last year board exam question. This is so simple question. Remember, we studied Wood's reaction. We studied Wittig reaction. We studied Wood's-Wittig reaction. What is Wood's reaction? Yes, you have an 2 halogen compound. Treating it with the metallic sodium in presence of again one more halogen compound. In presence of dry ether, you will get alkane with a double number carbon. You will get NX, you will remove this 2, will remove Na, you will remove this X, you will remove this X, will remove this 2, and we will combine this R and this R. You will get a alkane with a double number carbon. That is called Wood's reaction. We studied this is equal to Wood's reaction. Now, suppose you have chlorobenzene or any aryl halide, you have chlorobenzene, you are treating it with metallic sodium, again chlorobenzene. We will do the same reaction here. We will remove NaCl in presence of dry ether. You will get diphenyl. This is equal to diphenyl. We studied before, this compound is equal to biphenyl or diphenyl. This is equal to, Wittig reaction. We call it as Wittig reaction. This is equal to Wittig reaction. Remember, this is Wood's reaction. This is Wittig reaction. 2 halogen compounds, 2 alkyl halide, treating it with metallic sodium. In dry ether, you can remove NaX. Together, you can combine this R and R. You will get alkane with a double number carbon, that's Wood's reaction, to aryl halide with metallic sodium, and in dry ether you can say you will be getting biphenyl or diphenyl. Now if one of, now see here, this is equal to aryl halide, this is equal to alkyl halide. We are taking one aryl halide and one alkyl halide and doing the reaction with the metallic sodium, we'll get toluene. That is coming under Wurtz-Fittig reaction. The answer is Wurtz-Fittig reaction. Suppose you have alkyl halide here, CH3Cl plus metallic sodium plus the halogen compound you have, chlorobenzene you have. Now we are removing Na and Cl. We are in presence of dry ether. Dry ether, you will get toluene. This reaction we call it as Wurtz-Fittig reaction, right? This is equal to plus NaCl, 2NaCl. This is equal to Wurtz-Fittig reaction, right? So 2 alkyl halide will give you Wurtz reaction. 2 aryl halide will give you Fittig reaction. 1 alkyl halide and 1 aryl halide will give you Wurtz-Fittig reaction. So the answer here it is Wurtz-Fittig reaction. I hope you got it. This is an easy question, right? So we are moving to the next question. Which of the following has antiseptic property? Easy question. So chloroform. What is chloroform? Chloroform is equal to CHCl3. Bromoform. What is bromoform? CHBr3. Iodoform. CHI3. Pyrene is an uncommon name of carbon tetrachloride. CCl4, right? So now see, this is not common name. This little bit very rare name of carbon tetrachloride is also known as pyrene. So see, this is CHCl3. There is one more organic compound, namely pyrene. That's a aromatic hydrocarbon with 4 benzene ring. We are not talking about that. For the being time, chloroform, iodoform, bromoform, pyrene. Listen. Which of the following has antiseptic property? Very simple. Iodoform has antiseptic property. We heard about tincture of iodine. Iodine has antiseptic property. So iodoform has antiseptic property due to the presence of iodine, right? Iodoform has antiseptic property due to the presence of iodine. Remember, students, right? Yes, that's it. The next one we are talking. Which of the following is more reactive towards nucleophilic substitution reaction? See, we studied nucleophilic substitution. We studied SN1. We studied SN2. Now we know that aryl halides are less willing to undergo nucleophilic substitution reaction. Repeating, aryl halides are less willing to undergo nucleophilic substitution reaction. If you're talking about chlorobenzene, yes, if you're talking about chlorobenzene, this is chlorobenzene. If I'm treating it with aqueous NaOH, under normal condition, they will not react. They will look each other and laugh each other. Nothing will happen. So no reaction will occur if you are treating it with chlorobenzene with aqueous NaOH. Aqueous NaOH will provide OH minus, but chlorobenzene is so less reactive. We already learned. There are so many reasons we already studied. No reaction. So chlorobenzene with aqueous NaOH, no reaction. Now, suppose I am doing very drastic condition. Chlorobenzene with very drastic condition with aqueous NaOH at 623 Kelvin, then 300 atm pressure followed by acidification. It will react to produce phenol. This is possible at very high temperature as well as drastic condition. So they will react only under drastic condition. Chlorobenzene with aqueous NaOH react under drastic condition. That's it. Okay. So you will get NaCl. Now see, which of the following this reaction is called a nucleophilic substitution reaction because here OH minus is coming and replacing Cl minus. Normally aryl halides are less reactive, but we can increase the reactivity of aryl halides towards nucleophilic substitution reaction by introducing electron withdrawing group at ortho and para positions. See now, This is chlorobenzene, less reactive. This will be little more reactive because we introduced NO2 group at ortho. This will be little more reactive because we introduced NO2 group at ortho and para. This will be again more reactive because we introduced NO2 group at ortho, para and other ortho position. So this will be the order of reactivity towards nucleophilic substitution reaction. So the answer will be D. D is the answer. What is the reason? Most of them are struggling with the topic. Why this is more reactive? See student, this will react with even with the water. It will react with the water and warming. You will get corresponding chlorine is replaced by OH. So suppose you have this reaction. This is so highly reactive. I am writing the reaction here. You have the benzene ring here. We have chlorine with NO2 here. Again NO2 here. NO2 here. Yes, we are treating it with the water and warming. Water and warming. It is given in the reader. You will get a compound like this is OH. This is OH. This is NO2. This is NO2. This is NO2. This compound we generally call it as picric acid. Okay, 2,4,6-trinitrophenol is also called picric acid. This is highly reactive, so it will be the reaction can be done even with the warming with water. Water will provide OH minus and OH minus will react with the Cl minus to get phenol. So the reason secret for high reactivity of this compound is due to the presence of NO2 group at ortho and para. So you can increase the reactivity of aryl halide by putting NO2 at ortho and para, that reactivity towards nucleophilic substitution reaction. See now. Now, why? The reason is that two things they are telling. Number one, this NO2 group is electron withdrawing group. So, NO2 group withdraw electron from the benzene ring. NO2 group is withdrawing electron from the benzene ring. When NO2 group is withdrawing electron from the benzene ring, the nucleophile will attack the ring faster. Suppose this will withdraw electron from the ring. So when it is withdrawing electron from the ring, yes, electron withdrawing group is here. These groups are electron withdrawing group. They will withdraw electron from the ring. When they are withdrawing electron from the ring, the carbon atom become more electron deficient. So nucleophile will attack the carbon easily. So nucleophile can attack the carbon easily because that become more electron deficient due to the presence of this group. This group will take electron from the ring. So the ring become electron deficient. So nucleophile can attack over there. One reason is like that. Another reason that is bit harder for you. So another reason they told, you know, the intermediate ion generated during the mechanism of this reaction, there is an intermediate ion generated is called carbanion, that is stabilized by resonance. Okay, so intermediate carbanion generated over here is stabilized by resonance. Because of the two reasons, the NO2 group at ortho and para is more reactive. When chlorobenzene with NO2 group at ortho and para, it will be more reactive than other compounds. So here this is the order of reactivity. We can say here NO2 group with more number NO2 group, that will be more reactive. NO2 group is electron withdrawing group, that will increase the reactivity of nucleophilic substitution reaction. Okay, so that's about the chapter. We'll be back with another chapter next day. Okay.